So one of the things is, how do we recognize them, and how much do we need to know? So certainly if you know everything on the screen, you'd know everything you need to know. But that's a lot of information. You only have so many brain cells, and the exam's not that far away. So what's important? I would say know the names, but you don't have to remember both the technical name and the common name. As long as you remember one or the other, that's fine. If we say name that conic section, if you say saddle, we'll be fine with that. We'll accept that just as much as if you said hyperbolic paraboloid. And probably saddle might be an easier word to remember. Now, how do you recognize them? Well, the way you go about recognizing them, at least the way I like to, is I look at their shape. So I kind of know what cones look like. So they come together at a point. And then you have these nice, well, for lack of a better word, cones. Well, it's not very surprising. Now, ellipsoids, I put sphere here. A sphere is really a special case of an ellipsoid. But when we think of an ellipsoid, oftentimes we visualize a sphere. And I think we know what spheres look like. So bowls, they look like parabolas if you were to spin them around. And so you have these nice shapes. A saddle, those are, I would say that nowadays, if we were naming things, we probably wouldn't have called it the saddle. We would have called it the Pringle chip, and gotten some endorsement money from the, what is it, Frito-Lay that makes Pringles? I don't know. Whoever makes Pringles, we would have gotten a little bit of kickback from them. Okay, so the shapes aren't too crazy. An hourglass, that sort of has the shape where you have circles that get smaller and then get bigger. The hyperboloid of two sheets, I don't think there's a common name attached to it, and I couldn't figure one out. So yeah, just remember hyperboloid of two sheets. Now, the other thing, of course, is like, okay, if I see the shapes, I can usually figure out the common name, so that's not so bad. But what if I see an equation? How do I figure it out? Well, there's a couple of things. First off, we're not going to try to throw you something crazy where we do too much to it. So you're going to have something where you have the basic variables. You might switch them around. So for example, for the bowl, you might say x equals y squared plus z squared. All that's happening when you switch the variables around is you're just rotating your shape. So you're turning the shape maybe 90 degrees or something. So you're perfectly fine. The way I like to think about understanding things or remembering things is think about the cross sections. So for example, the only times that I see parabolas as cross sections are when I'm some sort of a paraboloid. So if I see a cross section that's a parabola, I know I'm either a bowl or a saddle. Then I say, okay, do the parabolas both go in the same direction? Like in the bowl, if I cross section one way, I'll see a parabola going up. But then if I turn 90 degrees when I cross section, the parabola still goes up. In a saddle, maybe when I cross section this way, the parabola goes up. But I turn 90 degrees when I cross section, the parabola goes down. That's when I know I'm a saddle. So if you see, aha, there's cross sections here which are parabolas, ask yourself the question, do the parabolas always go in the same way? Do they always go up, or do they sometimes go up and sometimes go down? So that's sort of the way to recognize your bowl or saddle. Look for parabolas. If every cross section you see is a circle, and when I'm talking about cross sections, let me be explicit what I mean. I mean things like x equals 0, y equals 0, z equals 0, which can't read very well with this pen because it's not a very dark pen. So I'll write it again because it's an important thing. Cross sections just means set one of your variables to a value, and really the only cross sections that you'll really need are what happens when x equals 0, y equals 0, and z equals 0. If all your cross sections look like circles, you're an ellipsoid or you're a sphere. In a cone, it's kind of interesting when your cross sections here, because your cone is coming together at a point. So you might be, oh, okay, I'm at a single point. If I move my cross section up a little bit, I'll see circles. If I slice this way, what I'll see is I'll see sort of an X shape where the lines come together. So you see crossing lines. For hyperboloids, that's if you're not a parabola or a paraboloid, and you see a hyperbola as a cross section, you're some sort of hyperboloid, then the only question you have to figure out is it connected or not. And for that, you just look in the cross sections. And if you see some cross-section where there's something in the middle, and there's nothing in this cross-section, it doesn't hit your surface, that means you're not connected. So you're a two-sheet versus one sheet. All right. That's all I have to say about that. Any questions about quadric surfaces? Okay. Now, we could stop here 42 minutes early, or I anticipated you might want me to do something else. So I can open it up for questions, or I printed out the most recent exams, and we can just sort of walk through the exam problems. I don't know what you would prefer.
I got one where you got to go from a line, you got to get to the closest point to that line.
Okay, so you want to get to the closest point to a line?
Yeah.
All right. So, sure. Do you have a specific problem, or should we just talk about it in general? We can make one up on the fly.
In general.
In general? Okay. So you have a line, and lines have the form x equals, say, I don't know, 2 plus t, y equals 3 minus 2t, and z equals negative t. Okay, so there's a line. And then you have a point, and your point out here, that's the point, I don't know, 3, 1, 0. Okay, so, no, that's a terrible example. 3, 1, 8. There we go. That's a good example. Now you might be saying, what was wrong with 3, 1, 0, Steve? It was getting too close to the line. I just want to make sure it's definitely not on the line. Okay, this one's definitely not on the line. All right. It doesn't matter. We're just talking generality. Now, there's a couple things you can do. So one thing you can do, there's two approaches. If you want to find, the question is, how do you find the nearest point? Now, there is a formula for distance, and you can apply the distance formula. The problem about the distance formula is then you have to remember something. And now you're running out of your brain capacity. It's running low. And then you have to memorize something. So it's like, okay, I don't want to have to memorize more stuff. So it's like, okay, so let's see if we can do it without remembering the distance formula. So here's sort of the philosophy. Say, hey, it would be kind of convenient to think that if I really want to find the closest distance, there's this notion of perpendicular. So if I were to draw the line segment connecting this point 318 to this line that I'm after, it'd have to be perpendicular. So this is an important idea. And we say, okay, so I know there's a sort of a perpendicular thing going on, and now we start thinking, what's perpendicular to a line? So what's the answer? What's perpendicular to a line? Right. The answer is it's a plane. So what we're going to do is we're going to make up a plane. And there's lots of planes. So I can form a plane that's perpendicular to this line. But in fact, I can form many planes which are perpendicular to this line. I can imagine it moving up and down on this line. Now, we're not just going to form any plane perpendicular to this line. We say, look, we want to settle on the plane that's perpendicular to this line. I should have drawn a little bit more conveniently. That also contains this point. So I'm transforming the problem. I was given a line. Next up, I find a plane. So to find a plane, what information do you need? A point. And the direction is the direction of the line. So the normal to our plane will be what? 1, -2, -1. So we get our plane, x minus 2y minus z equals something. The something comes from here. It's going to be -7. You plug in 3, 1, and 8. Now you say, okay, there's my plane. And what I'm after is the point where this line intersects this plane I just found. That's my closest point. So throw in your equations for x, y, and z for the line. 2 plus t, that's a t, minus 2 times 3 minus 2t, minus t equals -7, and then you start playing with things, and you cross your fingers and hope that things work out nicely. It's probably not going to work out nicely for us, but, you know, that's what happens when you try to make up problems on the fly. On the exam, we had a lot of time to think about these problems, and so they're much nicer. I think you end up with 6t equals -3, which, is that close? I don't know. We'll pretend like it's close, which means that you get t equals -1/2. And then, what do you do with this t equals -1/2? You plug it back into your line. So you end up with x equals 2 plus -1/2, which is 3/2. Y equals 3 minus 2 times -1/2. That's be 3 plus 1, which is 4. And z equals +1/2. So it looks like that should be our answer. And so that's the idea. That's the idea. So anyways, that's how I would do it. Now, the nice thing is, once you have the point, you could also now find the distance. The distance is a freebie. How do you find the distance from the line to the point? Yeah, use the distance formula between our new point that we found and that point there. So that you don't have to remember that distance formula. You say, look, as an intermediate step, I'll find a point. So that's how I would do that. Other questions that you'd like?
Distance formula? Are you referring to the one where you take the dot product to get to the perpendicular side?
You would. It's a cross product for the distance from a point to a line.
Okay.
Yeah. It's like you. Now you're going to try to make me remember the formula. So if you have a line with a point P, and then here's a point Q, and here's the direction vector of the line ABC. I believe it's, you take PQ, that vector from the point P to Q, you cross it with ABC, take that magnitude, and divide by the magnitude of ABC. That's the formula that I'm not asking you to memorize. But should you be like, I like memorizing stuff? Okay, cool, good for you. Yes? A sphere within two spheres? Well, what do you mean by an equation of a sphere within two spheres? There's like the quiz problem. So, generally speaking, if you're looking for a sphere, there's this list of things you do. So if you're looking for a plane, you make a list and you say, I need a point and I need a normal. If you're looking for a line, what do? Well, you say, I need a point, and I need a direction vector. And if you're looking for a sphere, what do? Well, you look for a center, and you look for a radius. So whenever you're asked to find a certain object, you start thinking, okay, what is it I need to get to make that object? So if you're looking for, say, spheres, you say, I need to have something like a center and a radius. So you can have a problem that says, okay, suppose you have, say, one sphere, and then you have another sphere. I don't know, let's put this other sphere inside of the big sphere. And then you're like, okay, I want to find the largest sphere that is not overlapping, so it's completely on the outside, or the exterior of the small sphere, but completely inside the big sphere. Now, if that was our problem, then we say, okay, let's think of it simpler. And the way we think of it simpler is you just say, slice it. It's analogies. Look, if a problem is throwing you off in 3 dimensions, think of a simpler problem in 2 dimensions. So the simpler problem in 2 dimensions is what? Well, not 2 spheres, but 2 circles. And now you say, okay, the key here is to say, okay, if these are our centers, what you do is you say, what's our radius going to be? Well, to figure out the radius, you say, okay, I can kind of say, if this is the direction I'm going, then what I want to do is I go from here, I find whatever this distance is, plus the radius And then, okay, what else do I have? I have this smaller radius in here, R1. So if I take the, okay, I'll call the big radius capital R and the little radius little r. So if I take the big radius plus the distance between the centers minus the little radius, that distance there, this is getting convoluted because I'm trying to make this problem up while we talk, that distance is there. In other words, it's the distance that I could go in between those two. So what is that? Well, that's our diameter of our new, well, circle, but of course in reality it's going to become a sphere. How do you get the radius? You divide by 2. And we say, okay, this is our new radius. So we're looking at ways to sort of combine information together to form our new sphere. Say, okay, well, now we've got our new radius. What do we do? Well, once you have our new radius, the only thing that's left is to find the center. And for that, you say, look, if I need to get to a point, or rather, I can say the following. If I need a point, I'm willing to settle for the following. Namely, how do I get to the point? So if I know how to get to the point, I know the point, because I can figure it out. So the way I can answer this question is, how do I start, and then how do I change? And change is a secret code word for vector. Because that's what vectors do, is they say, how do you change? So in this case, we would say, okay, well, maybe what I can do is I can say, all right, I can start from the center of the big sphere, and then I'm going to go in the direction opposite the other center, because that's the direction I need to go. But now I need to go a certain distance. And what's the distance? Well, the distance would be, I can think about it as going, I want to go just enough. So how far is just enough? And, well, you can say, look, if I go to R, I'll be out here at the edge. Then I just have to go halfway back the radius. So that's R minus R plus D minus little r over 2. This is the length I have to go, how far I have to move, but then I can also figure out the direction because it's opposite the other center. And then I put things together. So I mean, this is sort of like a quick hand wavy type kind of question, but essentially what are you looking for? Think of the geometry, think of how things fit together. Draw circles, make it simpler, think of the simpler problem, and that'll help guide you through it. All right. I should put that on the test next year. That'd be good. Or maybe it's already on the test. Whoa, who knows? Who knows? You'll know. 36 hours. No, 34 and a half hours. Then you'll know. All right. Any other questions? Yes?
Number 5 on the last exam.
Number 5 on the last exam. Do you know what it talked about? All right, I think I have that problem. Rewrite rho equals cosecant phi sine phi secant 2 theta in Cartesian, also known as rectangular coordinates. And there's a hint. Well, we may not give you a hint because, every generation is better than the one before. You guys are better at Calc 3 than last year's students were at Calc 3. Don't tell last year's students I said that. I'll deny it, of course. So, what do we have? Well, things might feel weird because you have these things like cosecant and secant. But, look, everything needs to be sines and cosines. And so you should know a handful of facts. So the handful of facts I remember, and they're enough to get me through all my conversions, is x equals r cosine theta, y equals r sine theta, and x squared plus y squared equals r squared. And thankfully, I learned this back when I took the last class, because this is just the polar formulas. So those aren't so bad to remember. The new ones that I need to remember are x squared plus y squared plus z squared equals rho squared. And then I'm going to have that z, or z, is rho cosine phi, and r is rho sine phi. So these are the new ones. So that's not so bad. Just essentially just 3 more new ones to add to the list, and then life is good. We can do that. Now, how do we actually go about doing these problems? Well, what we're going to do is we're going to say, I'm going to look for certain things. If I see a rho squared, I can handle that. If I see a rho cosine phi, I can handle that. And if I see a rho sine phi, I can handle that. Now, if I end up with an r, then I switch and say, okay, let me help polar to finish it off. So, it makes sense now to put everything in terms of sines and cosines, because that's the formulas. They have sines and cosines in them. So we say, okay, first step, rho cosecant. What's cosecant? 1 over sine. What's sine? Oh, it's sine. Okay, didn't have to do anything. That was good. Okay, what's secant? 1 over cosine. Now, we clear denominators, because fractions are not our friends. They've been stumping us for years. Darn you, fractions! Urgh. So we're going to clear them out. Say, be gone, fractions. I am done with you. So rho sine phi, cosine of 2 theta is equal to sine theta. All right. Well, interesting choices we have here. Now, we start to think to ourselves, well, what can we do? The 2 theta is a bother. None of these formulas have 2's on the inside of the angles. So we have to do something about the cosine 2 theta. What can we do with that? It's a double angle, cosine squared minus sine squared. All right, so you have rho sine phi is cosine squared theta minus sine squared theta. That equals sine theta. Say, okay, all right, we're getting closer. And now we start thinking to ourselves, all right, well, what happens here? Well, we have this rho sine phi. What's another way to say rho sine phi? R. Yes. So r times cosine squared theta minus sine squared theta equals sine theta. And hey, fun bonus, we've just done what? We've just put into cylindrical coordinates. Well, it's like, oh, too bad the problem didn't ask us to do that, or we'd already be done. But that's okay. And now we're like, cool. Now that we're in cylindrical, I go back to just my polar stuff, and I say, okay, what do I need? Well, boy, that sine theta just by itself is not good. What would I want there? Yeah, if I multiplied by r, and I have to do it on both sides, so you get r squared is r sine theta, or if we multiply it through, this will become r squared cosine squared theta, which is r cosine theta squared, minus r squared sine squared, which is r sine theta squared, equals r sine theta. And now I say, r cosine theta, is that on our list? Yes, it's x. That marks the spot. X squared minus r sine theta y squared equals r sine theta y. So there you go. All right. Good. Good. On a side note, do you know what kind of surface this is? This would actually be one that we didn't talk about. It's a cylinder. Now you might say, no, it doesn't look like a cylinder, Steve. Okay, let me rephrase it. It's a cylinder. See, now it's like, oh, okay, I see where you're going. Now here, the cylinder means there's a missing variable. What's not there? There's no z. So oftentimes when we say there's a variable missing, it's called a cylinder, even though it doesn't look like a circle stacked on top. It's actually a hyperbola just copied up and down. All right, any other questions?
Number 1
from the most recent exam? This one with this shape? Is this the right one? Okay. So find the total surface area, not volume. Well, that's interesting. They went out of their way to say what we're not supposed to do. All right. For all 6 sides of the parallelepiped, with the vectors corresponding to the edges, u being 3, 1, 0, v being 3, 1, square root of 10, and w being negative 1, 0, 0. And they provided a handy little picture so we remember what a parallelepiped looks like. Now, the way you should think about this problem is you should say, well, what do the sides of a parallelepiped look like? Well, 2 of them look like what's over here on that side. What is that? What shape is it? Parallelogram. Because the sides opposite each other are parallel. That's a parallelogram. Now, it could be a rectangle, but probably not. What about over here? What's this shape? It's also a parallelogram. And now, the really tricky one. The one on the top, what's that? It's also a parallelogram. So we say, you know what? Here what we have is we have 6 parallelograms. So, what are we after? We want to find the area of a bunch of parallelograms. Now we can save ourselves the work, and what we really have is 3 sets of 2. Because if I look at one side, there's a directly opposite side, which has the exact same amount of volume, exact same amount of area. So, this problem is about finding area of parallelograms and then just doing it a bunch of times. So if you see an area and you see the word parallelogram, what should cross your mind? The cross product. So what we're going to do here is we're going to do the cross product because, fun fact, if I have a parallelogram and say this side is u, that side is v, then the area is equal to the magnitude of u cross v. So what are we going to do? Well, we're going to take u cross v. I guess I should add little arrows here. And then I'm going to double that because there will be 2 sides that have area u cross v. And take that magnitude. Plus, I'm going to take 2 times u cross w. That finds the 2 sides which have u and w as the sides. Plus 2 times magnitude of v cross w. And then from here, it's just work. And you just work it out. So it's a bunch of cross products. And it's trying to test you, do you remember how to take your areas? I think from here, there's really not much insight gained after this step. So I'll stop here for this problem.
Can you do number 6 of this most recent exam?
Number 6 on this specific exam.
I had a question on this problem.
But there's a question on this problem in the meantime. What's the question on this problem in the meantime? Yes?
Why couldn't you do this 4 times u cross w? Wouldn't that be the same thing as very obvious cases?
No, it would not be the same. Yeah, you have to do them. You have to do each set of sides separately.
Okay.
So I think number 6 is this one, where you have curves intersecting at a point. And you want to find the. Is this the right number 6 that you're talking about? This problem? Yes?
Yeah.
Yes? Yes? Okay, I've gotten the thumbs up, which means I can talk about this one. So you have the curves R1 of t and R2 of s intersect at a point. And then it says, find the plane that contains the point of intersection and also contains the tangent lines of each curve at the intersection point. Now, we see a key word, find the plane. So when we're after a plane, we say, aha, I'm looking for a point. And then I'm trying to say, well, what point do I need? And it says, it tells me the point. It has to have the point of intersection. All right, well, that's good. I know what I'm looking for. But it also has to contain the tangent lines. Now, what's useful about that? Well, remember, I need to have a normal vector if I'm looking for a plane. And this says there's 2 curves, which means that there are 2 tangent lines. Now, to say the plane contains the tangent lines means that these vectors of these tangent lines, the direction vectors, are in the plane. Now, the problem is that these vectors in the plane are not the normal vector, because I need the normal vector to be perpendicular to the plane. How do I be perpendicular? Or how do I make something perpendicular? Yeah, cross product. So if you can find two direction vectors in the plane, then if you cross those two vectors, that makes a vector which is normal to the plane. So what happens in this problem? We have to go through and start figuring out what's the point and what are these tangent vectors. So for the point, the way we go about doing that is we say, okay, here's the idea. What we'll do is we have this set of coordinates. We have 5t plus 2 log t square root of 4 minus 2t minus t squared. That's the one curve. Then 7 square root of 2 s to the 3 halves minus 4 and e to the s squared minus s. So if they intersect, then the coordinates have to line up. So 5t plus 2 had better equal 7. Log of t had better equal square root of 2 s to the 3 halves minus 4. And the square root of 4 minus 2t minus t squared had best equal e to the s squared minus 2s. So whenever you have to find whether or not two things intersect, you say set the coordinates equal to each other. Now you have a system of equations and you solve. Now not all equations are going to be equally useful to work with. Some will be much simpler. So for instance, I'm kind of attracted to this equation. 5t plus 2 equals 7. Because that's the kind of equation I can solve. In particular, from here I see aha, and I don't have to write aha on the test, but I think it. That tells me that at the point of intersection, t had better be 1. Which means, coming in, I can plug in t equals 1, and according to this, I get r1 of 1. That would be 7, comma 0, comma square root of 4 minus 2 minus 1, which is the square root of 1, which is 1. So that should be the point of intersection. Now, I haven't yet proven that that is the point of intersection, but if there is a point of intersection, that's it. To prove it, what do I really need to check? I have to check to see if the other curve goes through that point, and which means I need a value for s. So I pick one of the other equations. It doesn't really matter which one. Let's say I pick the middle equation, and I say, look, I need to have 0 is equal to the square root of 2 s to the 3 halves minus 4. And we just start moving stuff around. That says that the square root of 2 times s to the 3 halves had better equal 4. I don't like having square roots, and there's really two of them here. There's the square root of 2, that to the half means the square root. I square both sides. 2s cubed had best equal 16, which means s cubed had better be equal to 8, which means the s is the cubed root of 8, which is 2. So we plug in 2, and what do we get? Well, you're going to get 7 and 0 and 1. You can check it. It works out. So now what do we have? We have our point. What don't we have? We don't have our tangent lines, and we need those because we need our normal vector. So, well, what's next? To find the tangent lines, what do you do? Yeah. So I'm just going to sort of wave my hands for the next few steps. You take r1 prime of t, which will be something. I mean, who knows what it is? It would take us a long time to actually take this derivative. So we're not actually going to take this derivative. But you could imagine that we did. So anyway, so imagine that we took that derivative. And then imagine that we did the same thing with r2 prime of s. And again, we really don't have time to go through and take that derivative. But if you did, you'd get something. So imagining that we've taken those derivatives, what's the next thing that you do? Plug in our points. We know when we're at the points. We don't have to take a cross product of these complicated things. Why do a complicated thing when a simple thing works? So r1 prime, you plug in 1. And you end up with getting something. And again, I mean, if we had time, we'd actually try to figure out what that something is. But we don't have time.
Doesn't that need to be to the negative 1/2?
Well, that's if we actually had time to take it. So, but anyways, yeah, you plug stuff in, and you hope stuff simplifies. And oftentimes, they do simplify. Okay, so you get to vectors, and then now what do you do with those? Yeah, so your normal vector would be r1 prime of 1 cross r2 prime of 2, which is, okay, at this point I really will stop. It's a cross product. That's your normal vector. Once you have your normal vector, you have your point. Put them together, you get a plane. All right.
Which point you use?
Well, it doesn't matter because it has to be the point of intersection. So if you're talking about a point, there's only one point that's a candidate for our point on the plane. Now, if you're talking about, say, there's a case that you could be in, which is you could imagine the following. You could say a problem where maybe you have two lines which intersect. And you want to find something where the plane that contains the two lines. Now, if that's the case, then you actually have a lot more freedom because you could say, okay, well, I have to find the normal vector, but I don't have to choose the intersection point as the point. Because here, every single point on the line is a point in the plane. I could just pick any point I want, and I'm good to go. But when I'm talking about curves, what's happening is the curves are moving through space. And so this particular plane will only really have just that single point because the curves are coming off of it. Whereas a straight line is going to stay inside of it.
For this problem, if you do cross product the opposite way, like it basically flips a vector.
Why would you do that? Why would you take a cross product in the opposite way? Yeah.
You get a negative answer, which is still correct, right?
Yeah, which is correct. Because you have to be careful, because oftentimes we'll talk about the normal vector, but the normal vector is the wrong word. A normal vector. Because normal vectors are not unique, because you can flip it by negating or you can scale it. It's still normal. The only thing we care about it is the direction. So normal vectors aren't unique. So yeah, if you switch the order, you'll still get the correct answer. Other questions? Well, we still have 10 minutes. So okay, let's do a speed run through the problems we haven't talked about and talk about what would we do. Find the distance traveled. So if you see words like distance, what are you going to think? Well, arc length. Okay, well that's really, it even helped you think that idea. So for arc length problems, they're pretty common. You're looking for things where there's a distance or an arc length. Your basic formula is the integral from a to b of the magnitude of r prime of t dt. Now, for magnitude of r prime of t, if we actually ask you to find something, what that means is that this is going to be a nice expression. So, how can it possibly be nice? Well, look for complete squares. You should be on the hunt for look, this is an integral. They told us we don't need anything past Calc 1 tools to do these things. And so that means that pretty much anything with the square root has to have a nice way to integrate it. So there's either something you can pull out and then do a u substitution, or there's a square. And so if you see 3 terms inside after you simplify, it's like that's probably going to be something fairly straightforward. Okay, so once you have that, this is pretty much the problem. Everything else is just computation. So that's that type of problem. A line passes through the origin and through the midpoint between a equals such and such and b equals such and such. Find cosine theta. Now, whenever you see a cosine theta, where do we see cosine theta? Yeah, dot is something we should remember. U dot v is equal to the magnitude of u, magnitude of v, cosine theta. So cosine theta, that's the u dot v over magnitude of u times magnitude of v. So we say, fantastic, I just need to find my right vectors. Now, notice they didn't give us any vectors. So we have to be careful. Well, what do we have? Well, what we have is we have these 2 points out in space. So we just draw a bad picture. A bad picture is better than no picture. And we say, okay, here's A and B. And we say, okay, there's the midpoint between A and B. And I'll say there's that midpoint. So we should know the midpoint formula. Just you average the entries. So that would be 2, 3, 4. And we want to find the angle between the line and the line segment between A and B. So here's this line segment between A and B. Whoop, imagine I could draw a straight line. And there's this line from the origin through there. So there's this angle theta. So what do? Well, you make angles. So you say the angle from the origin to the point. That's one angle, 2, 3, 4. But then you have to say, well, what's this angle here? Well, it's the angle from A to B, or it's the angle from B to the midpoint, or it's the angle from A to the midpoint. Sorry, I keep saying angle, but it's a vector. And you make a vector, and say we go from B to A. I don't know why I'm doing that, but I can. It's my right. It's my right as a mathematician. Okay, and now here are my 2 vectors, and I throw them into the formula, and life is good. Pictures are helpful. If in doubt, draw a picture. Okay. Find acceleration, a sub t and a sub n. Well, these ones are a bit lengthy, but there's not really much to them once you get the hang of it. Now, how do you do these? Well, probably the quick way to do these is you say, look, if I want a sub t, that's the derivative of the magnitude of r prime of t. And if I want the other a sub n, that I just remember a sub t squared plus a sub n squared is the magnitude of r double prime squared. If I can remember these 2 formulas, I can solve these problems. So how do I solve it? How do I actually go about doing it? Step 1, find your magnitude of r prime. Which means you find r prime, then take its magnitude. And simplify as much as possible. And you should be a little bit nervous because you're like, but Steve, look at this. There's cosines and sines. When you see cosines and sines, there's going to be a ton of cancellation. Or you're going to get sine squares plus cosine squares. You should be like, if you see sines and cosines and you're not getting tons of cancellation, you're doing something very wrong. Start doing something very right. No. Just be careful, all right? You should expect things to simplify. Step 2, find a sub t, because once you found this, you can get a sub t for free. Step 3, find r double prime squared. And then step 4, you find a sub n. These are all, no one step is very hard. As long as you can remember your basic setup, you're good to go. Okay. Well, now we can go even further back. So find an equation for the plane passing through some points, A, B, and C, and find the area of the triangle with vertices A, B, and C. So if you need a plane, you always say, aha, point plus vector. Point, we have a plethora to choose from. Which one is the right one? They're all correct. Okay, so you just pick one. And 1, 3, 8. All right, whatever. How do you get your normal vector? Yeah, you have these 3 points are all on the plane. What you do is make vectors. Say A to B, A to C. And then you cross them. Okay. You take AB, cross AC. There's your normal vector. And now life is good. You've got your normal, you've got your point, you've got your plane. If you want to find the area of the triangle, how do you do areas of triangles? Yeah, it's 1/2 AB cross AC. And you already did that in the previous step. You already found the normal vector. So it's almost no more work for you to find that area. The reason it's 1/2 is a triangle is half a parallelogram. Okay, find the point on this curve, blah, that lies a distance of 5 pi units along the curve from the point 0.46 pi in the direction of increasing arc length. Now this sounds a little bit complicated, but we see a couple key words. we see distance, we see arc length, and we're like, aha, this is like a distance arc length problem. The fact that it says distance and arc length being the key to figuring that out. Now, what does this have to do? Well, 0.46 pi, we say, okay, that corresponds to a certain time. What time would that be? So, for what t does 4 sine t equal 0, 4 cosine t equal 4, and 3 times t equals 6 pi? The answer is 2 pi. You just picked an entry that's easy to compute. So it says, hey, I'm at time 2 pi, I'm at 0.46 pi, and I've gone a distance of 5 pi, which means starting at time 2 pi up to some distance, up to some other time b, which is not known. So this is unknown right now. The magnitude of r prime of t, dt, I get 5 pi. Well, what does this allow me to do? This allows you to solve for b. It'll turn out that this is a very easy function to integrate. You can now solve for b. Well, what do you have when you solve for b? B is a time. What do we want? We want a point. So what do? Plug it back in. So let's see. What are some other things? Let me talk about one or two more. And find the osculating plane. Osculating plane is pretty simple because we need it to have a point and it has to have two directions. So what it is that r at 0, because it's time 0, that's your point. Your normal, you take r prime cross r double prime, and that's your normal. Because that way it'll contain velocity and it'll contain acceleration. Once you have your point and your normal, life is good. And this one I just like because we've done it before, but students freak out about these types of problems. Don't freak out if you see a problem like this, where you have this weird, complicated story. Don't get caught up in the story. It's a beautiful story, and we always appreciate the pictures, you know. Channel your inner artist, that's fantastic. But don't let it intimidate you. Say, okay, there's some curve. All right, I know the curve. And now you say, all right, I have to do something about a tangent line. And almost always these types of word problems where you have a curve, it's like there's a tangent line involved. In this case, you have this ship, it's flying to a space station, it's cutting off the engines, which means it's going to go straight. And so you're like, okay, how do you solve these problems? Well, the answer is you say, if I'm trying to hit this space station, which I guess is now a Borg ship because that's what I can draw in a hurry, you want to try to just make sure the tangent line finds that property. So, if you're after one particular tangent line, what's your best strategy? So you're after a tangent line with a certain property, what's your best strategy to do? Find every possible tangent line. Find all the tangent lines. And then what you do is, once you found all the tangent lines, pick the one that's good. Now you might say, how in the world do I find all the tangent lines? Because I only have 75 minutes and one piece of paper. And the answer is, you say, look, all tangent lines have the form r of t plus s times r prime of t, where t is just something that hasn't been chosen yet, and s is some extra parameter. So these are all the tangent lines. And now find the one that does what you need. And if you remember that, this problem suddenly becomes not intimidating at all. And it's like, I'm going to get my points. I'm going to get all my points, and I'm going to do great. Because I'm a good student. All right. Good luck. See ya on the other side.